Good morning or good afternoon, everyone, whichever is the case. Welcome to this Networking Friday session, thematic session on nanosatellites. My name is André Oliveira. I'm from the Collaborative Laboratory Plus Atlantic here in Portugal, and I'll be moderating the session today. This is the third session of the year. We have 249 registrations from 36 countries, so welcome everyone. And a special welcome to a class of students from the Ocean Sciences and Techniques Academy from Egypt, which is led by Professor Mohammed Adel. Today we have a very distinguished panel of four panelists. We have Roger Walker from ESA. He's the head of the CubeSat Systems Unit. Ernest Matey from All Nations University Space Systems Technology Lab in Ghana and representing the African Constellation Satellite Project. Milton Kampel, senior researcher at the National Institute for Space Research in Brazil, INPE, and Stewart Bernard, chief scientist at the South African National Space Agency, SANSA, and also chief scientific officer at the ESA Center. They will be joined in the end by Miguel Beló, the CEO of AIR. And just before we kickstart the different sessions, I do have a couple of slides just to introduce you to the Collaborative Laboratory Plus Atlantic, because I'm sure that most of the audience doesn't know us. Just gonna try and share my screen. So I hope you can all see my screen. Basically, the Collaborative Laboratory Plus Atlantic is a non-profit association based in Portugal that's comprised of 13 members between academia, universities, research institutes, and industry. We have 4 facilities in Portugal, 46 highly qualified staff with a very multidisciplinary background. We have oceanographers, marine biologists, engineers, mechanical and electronic, aerospace engineers, geologists, architects. So really a very multidisciplinary team. And we're one of the Portuguese nodes of the AIR Center. We work essentially in the nexus of trying to generate value, knowledge for a sustainable ocean. And some of the areas of work we've been focusing on are mostly related to the integration and combination of remote sensing data, especially concerning the use of small satellites and constellations, as well as numerical modeling and artificial intelligence, both using global and coastal products such as MEMS, the Copernicus Marine Service, and also results from models from our own members, in situ data and citizen data, where we've been working on projects with some of our association members. Also have a collaboration with the MIT Visualization Lab to test some of the sensors they've been working on. And we're mostly interested in democratizing access to oceanic sensors and combining all of this with socioeconomic data to try and provide intelligence and new knowledge for different application areas, ranging from aquaculture, fisheries, coastal hazards, renewable energies in offshore locations. So we cover a very broad range of activities. And this is basically what I had to say about Plus Atlantic. I don't want to bore you too much. So we'll jump straight into the different presentations. And I'm most pleased to give the floor to Roger from ESA's CubeSat System Unit. Roger, the floor is yours.
Thank you very much, Andre. I'll just share my screen then. Okay. Is that good to go? Can you see that now?
Yes, perfect.
Okay, perfect. Well, good afternoon, everybody. Good morning, good evening, wherever you are. And yes, I'll give you a talk on technology CubeSat nanosatellite activities at ESA. My name is Roger Walker. I'm head of the CubeSat Systems Unit. I'm located at ESA in the Netherlands, and I'm working for European Space Agency in the Directorate of Technology, Engineering and Quality. So just before we get into the activities we're doing at ESA on nanosatellites, I just wanted to perhaps give a few introductory words by way of a tutorial about CubeSats, nanosatellites. So just to introduce you to CubeSats, if you don't know what they are small satellites of standard external cubic unit dimensions, and they're always launched inside a container on the launch vehicle. Okay, so here you can see the different sizes of CubeSats on this this chart. One CubeSat unit, or 1U, is approximate to 1 liter, or 10 by 10 by 10 centimeters. So the smallest CubeSats around are 1 unit CubeSats, around 1 kilograms, going all the way up to, well, 16 units and 27 units are being considered now. So we've got the whole mass range covered from 1 kilograms up to around 50 kilograms. The most common CubeSats at the moment are 3, 6, and 12 units, as I'll show you. And they are basically small satellites, which are, as I said, standardized in dimensions, but highly modular in terms of how they're integrated with the electronics and all the onboard systems internally. And they're extensively using commercial off-the-shelf electronics components, so components that have been developed for terrestrial uses, automotive, etc. And all of those things, small size, modularity, standardization of interfaces and terrestrial components combine to keep the cost low. So why are we interested in CubeSats in general? They are low cost. They're some of the lowest cost spacecraft available to develop, launch and operate. They are also fast to develop. Typically we would develop a CubeSat in 1 to 3 years, depending on the complexity and what technology needs to go into the CubeSat to be flown. So those two factors, low cost, fast to develop, make them ideal for technology demonstration. They're also a driver for technology miniaturization as well, because if we can access space with these very small platforms cheaply and quickly, we want to stimulate the development of technologies and spin in technologies from other sectors that are highly miniaturized. Over the years, the capability, therefore, has been increasing of these small platforms, and now they've reached a level where they can be deployed due to their low unit cost in highly distributed systems. So I'm talking about constellations, swarm formations, or fleets of CubeSats and so on. So these are particularly interesting, let's say, applications of these distributed systems for various purposes, which I'll get on to explaining. If we look at CubeSats in Europe and how they've evolved in the last years, we had CubeSats in general have started in the education domain at universities since 2005 in Europe, and they continue to this day to be very good educational tools for hands-on education for engineering students. Typically they're 1 to 3 unit CubeSats. But over time, since around 2010, CubeSats have been used quite a lot for technology demonstration. So this is the second wave of CubeSats. You could call it an experimental wave, where not only universities are experimenting, but also industry, small companies spun off from universities, and also space agencies like ESA, but other agencies in Europe and around the world. More recently than that, as the capability of these small systems have been demonstrated with the technology demonstration missions, we're now starting to see a third wave a so-called operational wave, where CubeSats can be fielded for various applications. For instance, in low Earth orbit for constellations or swarms, close proximity operations, formation flying, rendezvous and docking, or close inspection of other objects in space. So that's close proximity operations. And also more recently, only the last couple of years, we've seen them being developed for science or exploration beyond low Earth orbit. And again, CubeSat sizes have been growing up to from 3 up to 12U in this context. So for the educational CubeSats, I mean, I've been with CubeSats since around 2007, and that was when the CubeSats were being developed at universities, and we at ESA offered the opportunity for 7 university CubeSats of 1U size to be flown on the maiden flight of our Vega small launcher, and that happened in 2012. You can see a picture here of the team with 3 of the CubeSats being integrated into its pod deployer. So that was really the genesis of CubeSats in Europe at that time. As I said, the second wave technology CubeSats, that's something I've been leading since 2012. And our first technology CubeSat to be launched was, as you can see here, GOMX3. Was a 3 units CubeSat. Here it was developed from the project kickoff to flight readiness in 1 year, so quite a fast project. And then it was deployed from the International Space Station in October 2015. And it spent 1 year in orbit demonstrating various technologies on board the CubeSat, and that was including 3-axis attitude control, also software-defined radios, on board, and receivers for tracking the aircraft, the signals broadcast by aircraft in flight as well. Then we moved on to the second project. This was aimed at first generation technology demonstration for constellations. GOMX4B was the name of the project. That was launched in 2018. You can see the CubeSat here was double the size of GOMX3, so it's a 6-unit CubeSat. And this flew with GOMX4A, which was funded through outside of ESA, but the 2 CubeSats were operated in a tandem mission together, and they demonstrated successfully orbit control with CubeSats using propulsion for the first time. Inter-satellite links between the 2 satellites up to distances of around 4,500 kilometers. A technology which is very relevant for constellations to get data back to ground quickly through the constellation. It had demonstrated the first hyperspectral imager on board a CubeSat, and also a star tracker for precision pointing. Then we've had also in development CubeSats for scientific research. Probably it's good to highlight a couple of these. One of these is Picasso. That's for atmospheric science. So it's a 3-unit CubeSat that was launched in September last year to demonstrate the measurement of stratospheric ozone, vertical profiles of ozone, using a multispectral imager. Its sister satellite, Simba, was also launched on the same launch in September last year, and it was carrying a payload to measure total solar irradiance and the Earth albedo and infrared emissions. So essentially looking at the Earth radiation imbalance, which is a quantity very relevant for climate monitoring, of course. And then we have another couple of CubeSats, one for space weather monitoring to be launched next year, and we have already launched a CubeSat for atmospheric re-entry research called Carmen. I wanted to bring to your attention another CubeSat we have in development at the moment. I understand quite a few of you are in the marine science and the marine community. We are developing a CubeSat, 3-unit CubeSat called Pretty. It's for demonstrating GNSS reflectometry techniques. So the CubeSat will carry a payload which is essentially a receiver for GNSS satellite signals, so GPS or Galileo signals, and it will pick up signals that are coming directly from a GNSS satellite, and also the same signal bounced off and reflected from the ocean surface, on the surface of the ocean there. So that's all measured in a software-defined radio on board, and through onboard correlation techniques, it's using the direct and reflected signals to actually measure the sea surface state, quantities like the roughness of the sea, the presence of sea ice, and also it's performing relative altimetry, so it's measuring ocean currents at high precision, typically on the centimeter level of relative altimetry. So that's going to be a CubeSat that's launching in 2022, so it could be quite relevant for the marine community. So that's a bit of a highlight of the technology CubeSats we have in the program. Coming on to the operational wave, as I said, there are different applications. We have done quite a lot of studies on future low Earth orbit constellations, and particularly for Earth observation and telecommunications purposes. So for Earth observation, there have been some very interesting studies on constellations for high resolution NO2 pollution monitoring of urban areas over the diurnal cycle. So a constellation of typically 30 satellites in different orbit planes could monitor over the daily cycle NO2 and also methane emissions. All of these are relevant for pollution in urban areas, plus climate quantities and so on. There are other applications for CubeSat constellations, particularly in global tropospheric measurements for weather prediction. So that's another aspect very relevant for shipping and marine aspects. That's done using GNSS radio occultation, sounding of the atmosphere, and reflectometry, which I mentioned also. Payloads are consisting of microwave radiometers, for instance, will also be useful in this context. Then you have optical imagery payloads that could be flown on these constellations for performing change detections, particularly of land, floods, and fire hazards, and that's served by payloads of hyperspectral images. In the telecom domain, this is done in our ARTES program. There are quite a lot of studies being done and missions, demonstration missions ongoing on narrowband in-orbit of things, asset tracking for assets on ground, ship and aircraft tracking, so essentially SAT AIS and ADS-B signal tracking, and also situational awareness. We've also looked at constellations for space weather monitoring, particularly the ionosphere, radiation environment, and the Earth's magnetic field. From all of these studies, it's been highlighted that larger platforms are becoming more relevant, so 12 to 16U for more payload volume. We also need to have capabilities to reorbit or deorbit the satellites at end of life, and have high rate downlink to get the data back to Earth quickly, and also into satellite links, as I mentioned. And some technologies have been highlighted, for instance, higher power generation for communications, downlink, and electric propulsion for maneuverability. Not to mention also increases in onboard autonomy are needed for managing a large constellation. For close proximity operations, we have a very interesting mission to be done in the next few years. The Rendezvous Autonomous CubeSats experiment that's aimed at demonstrating the docking of two CubeSats, 6-unit CubeSats in orbit. And the demonstration is aimed towards future applications like autonomous on-orbit assembly of larger space structures using building blocks. So you can imagine after this demonstration would be done, we can start to contemplate building up things like large optical telescopes from several mirror segments on orbit. So that's a way of aggregating space systems and doing on-orbit assembly. Then we move to deep space. So we are doing developing some deep space CubeSats. There is a deep space mission for planetary defense purposes called the HERA mission. That's to be launched in 2024 to visit the asteroid Didymos. HERA is a large spacecraft of around 1 ton, and you can see that on the image here at the top. That spacecraft will be carrying two 6-unit CubeSats, which will be deployed once the main spacecraft arrives at the asteroid. And you can see the two CubeSats depicted here. And those CubeSats will be carrying very interesting scientific payloads to, for instance, measure the interior of the asteroid, which will be the first time ever a small body, an asteroid in space, has had the interior composition measured using low-frequency radar. And also the other CubeSat will be carrying multispectral images characterizing the surface mineral properties. So that's one good example. The other example to highlight for future deep space CubeSats is a mission we're now starting the preliminary design phase. It's the Miniaturized Asteroid Remote Geophysical Observer, MARGO. And this is a concept which is a 12-unit CubeSat, and it will be a completely standalone system. So it will be completely capable to independently explore deep space and rendezvous with an asteroid. We plan to complete the preliminary design early next year, and once the funding is secured for the development phase, we plan to launch the CubeSat in 2024. So this is our flagship project, and it's carrying a number of highly innovative miniaturized technologies, such as let's say electric propulsion system, X-band communications with an X-band high gain antenna, which you can see here on the graphic, and also a high power solar array, which is steerable towards the sun to maximize the power generation. So that's a very ambitious and technologically challenging mission, but we have all of the technologies in development right now in our program. And once they're integrated together in a complete system, we'll launch the CubeSat, and it will arrive at the asteroid around 2 years later to measure the asteroid for the presence of in situ resources, so minerals and water ice content that could be potentially mined in the long-term future. The point to highlight here is a mission like MARGO will demonstrate a system which will lead to the entry-level cost of deep space exploration being lowered by about a factor of 10. So typically to rendezvous with an asteroid currently with conventional technology, it might cost around 250 million euros. And we aim to lower that cost to around 25. So it's quite a radical reduction in cost for deep space. And that will lead to many different applications for this type of system in the future, not only asteroid missions, but also potentially missions to Mars, Venus, or also measurements of space weather in deep space. And that concludes my presentation. Thank you.
Thanks very much, Roger. Just a quick note from my side. If the attendees can post their questions directly in the Q&A window, I forgot to mention this in the beginning. We'd appreciate it very much. So next up, we have Ernest Matey, who's representing the African Constellation satellite project. Ernest, the floor is yours. Ernest, you're on mute.
Yeah. Can you hear me?
We can hear you.
Okay. Great. So thank you for your presentation. So I'll Hello?
Yes, we can hear you, but the connection is not that good.
So you cannot see my screen?
We can see that you started sharing your screen, but me personally, I only see a black screen. Ernest, I propose we try to solve this issue. And in the meantime, we'll move on to the next talk. Is that okay?
Okay.
Perfect. We'll come back to you in a couple of minutes. Then I propose we move on to Milton Kampel, senior researcher at INPE. Milton, the floor is yours.
Thank you, André, Miguel, and José Luis. I will share my screen from now on, and my presentation is indeed recorded, so hope you can follow, hear it, and enjoy it. I'd like to thank José Moutinho and the organizers for participating in this Network Friday thematic special session on nanosatellites promoted by the Air Center, and greet the colleagues who make up this section and the audience that honors us with their participation. I am a senior researcher at the National Institute for Space Research, INPE, head of Motions Lab, and INPE is a civil body of the Ministry of Science, Technology and Innovation of Brazil, whose competence was updated in September 2020 as to develop scientific research, technological development, operational activities and capacity building in the fields of space and atmospheric science, Earth observation, weather forecasting and climate studies, space engineering and technology, and related areas. INPE has its headquarters in São José dos Campos, state of São Paulo, and has other facilities and infrastructure in different places in the Brazilian territory. According to the new internal organization chart, the areas of Earth observation, Earth system science, weather forecasting, and climate studies are now encapsulated in the new Earth Science Coordination where I work. I think it's interesting to comment on the creation of a new small satellite division in the Coordination of Space Engineering, Technology and Science, whose chief is Engineer Antônio Carlos de Oliveira Pereira Jr., whom I thank for the shared material here. It is interesting to celebrate the success of the CBERS 4A satellite for 1 year in orbit, launched in cooperation with China. Images from the MOOCs, WPM, and WFI cameras are generated and distributed routinely with revisit of 31, 31, and 5 days, swaths of 95, 92, and 684 kilometers, with 4 multispectral bands in the blue, green, red, and near-infrared, with spatial resolutions of 16, 8, and 55 meters respectively. The WPM camera also has a panchromatic band with 2 meters resolution. This mission is part of a family of satellites started with CBERS 1, followed by CBERS 2, 2B, 3, 4, and 4A. Here is an example of a CBERS 4A WPM image of Angra dos Reis at the southern coast of Rio de Janeiro state, acquired in August 2020, shown as the fusion between the panchromatic and the multispectral bands in green, red, and near-infrared. Now we have the same image as a different color composite, blue, green, red, zooming over Itaorna, where Brazil has its nuclear power plant. Here we can see another CBERS 4A WPM image of Cabo Frio region, showing part of the Araruama Lagoon and the coastal region. And here is a zoom of the previous image, showing the port of Forno and interesting wave patterns at the Boqueirão between the continent and the Cabo Frio island. We are looking forward to the launch of the Amazonia 1 satellite, the first to use the multi-mission platform developed at INPE with a focus on monitoring deforestation and vegetation cover. The launch is now scheduled for February 28th at 01:54 a.m. local time in Brasilia. We also have more than 60% ready for an upcoming mission on the multi-mission platform, but still awaiting some important definitions. We hope for an ocean observation mission, which could be in the visible and infrared range or in the X-band of microwaves. INPE's Satellite Tracking and Control Center consists of an integrated set of facilities, systems, and teams whose function is to plan and execute the tracking and control activities of national and international satellites. It encompasses the entire ground segment for INPE's satellite control, operating 24 hours a day, 7 days a week, comprising the Satellite Control Center in São José dos Campos, the Cuiabá Earth Tracking and Control Station, and the Alcântara Earth Tracking and Control Station. The 2 main receiving stations for Earth observation satellites are located in Cuiabá and in Cachoeira Paulista. Here we can see the respective footprints of the antennas. In Cachoeira Paulista, INPE maintains its Cray XC50 supercomputer and a remote sensing data center with a capacity of 6 petabytes. The Integration and Testing Laboratory, LIT in Portuguese, contributes to Brazil's progressive autonomy in strategic areas, providing technical support to the efforts of the national productive sector in developing its competitiveness in the international market. LIT helped to create the necessary environment for the promotion of national space programs and in cooperation with other countries, providing high-quality, low-cost, and timely service, and providing testing and metrology service to the industry. Here, we can observe the experience in assembly, integration, and tests, AIT, of different satellites, not only Brazilian, but also from other countries and agencies as well, including small satellites. It is worth highlighting the experience acquired in the area of space development. The scenario of small satellites in Brazil started with the development of Nanosat BR1 in cooperation with a university from the south of Brazil in 2014, followed by another cooperation with the Aeronautical Technological Institute, ITA, from the Air Force. Other missions followed in collaboration with other universities, institutes, private companies, and agencies, both Brazilian and international, including a municipal school, until the first constellation of CubeSats under development. The Floripa Nanosat was launched in tandem with Sirius 4A satellite. It is worth mentioning other interesting initiatives, such as the events of Cube Design, whose third edition took place online in 2020. This event also supported INPE's first ArtSat workshop for lovers of space poetry or nanosatellites for artists. In 2021, Cube Design is organizing an event to receive cartoons and comic books about space missions. In addition to encouraging creativity, Cube Design wants to engage younger age groups in the space area. Based on the development carried out, it was possible to develop an ecosystem of small satellites based on principles of research, innovation, and development involving the academic sector and the funding agencies, integrated with an industrial policy with a focus on offering services and applications of broad interest or social benefit. The basis for the production of small satellites at INPE involve the conceptual architecture of a standard space mission with all segments and components considered important, as well as the life cycle of a complete space mission. INPE does not develop the launch vehicle, and since Brazil does not yet have satellite launchers, we hire commercial launchers or reach the space through international collaborations. The requirements of small satellite projects and programs demand a mapping of stakeholders, a diagnosis of as-is, the strengthening of themes considered essential, and planning of how to be. Technological challenges are identified and addressed, considering the development needs, what data is being demanded by different areas, and whether there are technologies to be validated. In terms of proposals for advancing small satellites, we must consider the training of young people and others interested in entrepreneurship. One idea is to create a center for incubation of technology-based companies on nanosatellites. From there, it would be possible to offer technical support, mentoring, networking, training and qualification, and transfer of know-how. We must also consider the creation of demands in this sector. In addition to actions such as Cube Design, with its fourth edition scheduled at INPE for 2021 and collaboration models, it would be important and interesting to participate in mission programs such as the Constellation proposed by the Air Center to leverage the development of Earth observation nanosatellites. In any case, it is necessary to define the payload or the type of instrument of each mission. We are aware of the efforts made in the Air Center to understand the demands and requirements of member countries interested in initiatives like this. In any case, we understand that the Earth observation community is also formed by empowered experts with a willingness to share and reuse knowledge, which increasingly uses cloud platforms, demanding a flow of observational in situ and multi-satellite data to help build or even just use tools or APIs that meet the scientific objective, services, and applications envisioned. Finally, I'd like to mention some examples of efforts made at INPE in the areas of education, outreach, capacity building, and dissemination of knowledge, including face-to-face and distance learning courses, graduate programs, technical and scientific events, development of free software, and research and development activities. Let me thank my colleagues Antônio Carlos Pereira, Ivan Barbosa, Maurício Ferreira, Laércio Namikawa, and Walter Abraão for sharing materials and information. I thank everyone for the audience, and I'm available for questions. So yeah, that's what I have for now. So thank you very much for your attention.
Thank you, Milton. Very interesting presentation. I think, shall we try again, Ernest? Let's see if we'll come back to all the questions at the end of the sessions. And again, if you can please post your questions directly in the Q&A window, we'd appreciate it very much.
Okay.
Perfect.
Jose, thank you for sharing my slides for me. I think the network over here is very good.
Well, we're still having difficulties connecting to Ernest, so we'll move on to Stewart and try to come back to Ernest afterwards. Stewart, the floor is yours.
Okay, thank you very much. Let me just share my screen here. All right, are we good to go?
Yeah.
Okay, excellent. So thank you very much. My name is Stewart Bernard. I'm Chief Scientist in Earth Observation at SANSA. Thanks to the Air Center and to Jose in particular for all his organization. So before I talk about nanosatellites in particular, I actually need to introduce you to our new space program, which is called the Space Infrastructure Hub. And I'm going to start with this very, very simple slide, which basically focuses on the fact that this is developing products and services that directly respond to sectoral user needs, and the building of space infrastructure, which is both the enabling ground segment, the mission ground segment, and obviously the space-based assets. So you can see it's fairly operational in focus to some degree. Now, this is a bit of a game changer in South Africa because this is the largest funding injection at about $300 million that we've had. It's really the first time we've gone on to a kind of mission-focused space service provision. It's very outward looking from SANSA. Most of the money is destined to be spent in the South African industry, upstream and midstream and downstream, and to enable that industry to grow it sustainably, and of course to provide the products and services not only to government, but also to the private sector, and to try and greatly increase the uptake of space-based products in the business and consumer sector. And in South Africa in particular, one of our interests is inclusivity and transformation. So to really try and kind of get right at the end of the downstream to get a much greater sense of ownership around space products. What does it look like? This is a very kind of brief conceptual model. There's a set of hierarchical requirements, obviously, that drive the various components. Much of the downstream value is obviously created by the existing sensor portfolio. So this will include things like the Sentinels and Copernicus, NASA, NOAA, BRICS missions, etc., etc. These go into things like analysis-ready data cubes and data exploitation services with industry enablement mechanisms, incentivization mechanisms to develop both public service platforms for government and more enterprise solutions. Obviously, there's the upstream, the new missions, which a large part of the budget is focused on. A little more on that later. And then obviously the R&D as well, which will focus on anything from development of AI to hyperspectral to more kind of user-facing components. This slide is really just to show you that there's a kind of hard edge, and there's a kind of analog here with Copernicus in that the agencies don't go beyond about a level 2 in the downstream. A similar mechanism is envisaged for SANSA to ensure that the other components actually are benefiting from it, and it's not too inward looking or okay, this is a kind of blow up of the upstream part of it, and the main take-home message here is that in addition to these kind of knowledge-based services, the decision support services in the downstream, we've got two main sources of innovation, which are the various upstream missions we're anticipating, which come through obviously a requirements process, and the research. So those will create deltas in innovation and a breakthrough in user needs, which will talk to our metrics for determining how successful we are. And if we go to the downstream, this is basically where we're anticipating, I hope, seeing at least 50% of our economic impact. So various mechanisms to encourage exploitation. These grayed out boxes are the revenue aspects, which I don't really want to talk about here, and various ways for industry to get to the public service platforms. Okay, so that's a very quick summary of conceptually where we're going with the Space Infrastructure Hub. Here's a very quick example of kind of how we see value being created. And I've chosen agriculture here, but you know, a fisheries type value chain would have a quite close analog. So we have a series of existing missions that we can get data from. We have new upstream missions. They go into cubes, industries involved in there. That goes into kind of co-designed the midstream and downstream systems, which provides then a very wide range of products that are driven by the sectoral user needs, and that goes into various levels of government and effectively into kind of farm level management. And the idea here in the private sector is to basically lower the entry point to smart farming. So we'd see that it would influence anything from financial sectors, insurance, you know, risk management, productivity, et cetera, et cetera. Okay, now if we think about nanosatellites, obviously there's a very strong interest in nano and microsatellites. And Roger, thanks very much, Roger, provided a very good outline of exactly why this is, the lower costs, the rapid development and evolution cycles, the technological advances, obviously the constellation scaling, etc. So South Africa has a fairly strong nano and microsatellite heritage, more on this shortly, but the main point is at the moment, we are not in a position to say exactly what we need because we have to go through a series of processes based upon the various levels of requirements in the program. So it's quite a dynamic space. And this process looks something like this. First of all, we have some program requirements. So these are the largest in the broadest brush terms. And these are driven by a combination of primarily economic impacts, both in the broadest possible sense, the catalytic impacts to the industry. In other words, are we making the industry sustainable and attractive? Some of the downstream ownership aspects, you know, the non-monetized societal aspects. These are informed by studies that are being commissioned right now, economic studies, landscape assessments, capabilities, etc. And those then cascade into some upstream user requirements, research and downstream requirements. And you know, the key thing is that a lot of what we're doing here is to make South African industry viable and attractive active in addition to trying to realize downstream economic value. But we also obviously can only build what domestically we're capable of building. So much as, for example, we might wish to, as a mad scientist, to develop some, multi-wavelength LiDAR on a CubeSat, that ain't going to happen. Those upstream requirements translate into some sectoral user requirements. There's some iterative industry engagement, and then we would see some SANSA missions, and then we're also looking at potentially some hybrid kind of venture capital missions. So part of the Space Infrastructure Hub is the enabling infrastructure on the ground. One of the main ones we hope is this new concurrent design facility. Here are existing European examples, and we hope this will very much speed up the development, obviously, which is a key thing in small sats. Similarly, for assembly, integration, and testing, there's a lot of investment in either new facilities or upgrading existing facilities that are needed to enable both the component industry and the mission industry to become more competitive, and obviously to realize our own domestic missions. Okay, so some examples of the capabilities. So the first one I'll show you is called ZA-CubeSat. It's in space at the moment. It's a 3U satellite. It's in the maritime domain awareness space with primarily a AIS payload. It's getting us towards the VDES, which will be in the new Constellation. It's funded primarily through government and the university, the Cape Peninsula University of Technology, rather than private sector. And that will phase into 9 satellites that will provide a VDES service and give us a much better maritime domain awareness capability, and of course the actual V capability to maritime users. This slide is in here because I like the fact very much that the ZA-Cube data is actually being operationally assimilated into our fully operational integrated vessel tracking system under our Ocean and Coastal Information Management System. So there is a downstream segment that is integrating the data. And this just shows the kind of cumulative success and some of the lessons learned, but basically the fact that we have been able to successfully use a very large amount of data from the single satellite. And then obviously as we upscale to a 9-satellite constellation, we'll get to the kind of revisit times that we would like to be fully operational. So the next example is private public, and this is a series of CubeSats of different sizes with optical payloads. InSight 1 is, the mission has now ended. This was a very successful first mission in the EU's QB50 with an RGB imager. InSight 2 and 3 are slightly larger satellites that'll be launched in the next few years, and they will bring a more advanced imaging capability. And as SANSA, we're very pleased that we have such a strong optical imaging capability as part of our homegrown industry. And the attractive thing about InSight is that it effectively has a research aspect to it, and we'll return to these questions. But when you start looking at, for example, hyperspectral on very small platforms, there's a lot of instability, and there are a lot of lessons to be learned about how to optimally go about the sensor and bus design. So you're not just getting jittery images, etc. You can employ things like TDI techniques, etc. Similar goal to the second one, platform stability, and then some other goals relating to the production of domestic power units for CubeSats and around radiation hardening. So InSight 1 was considered very successful. It spent about 3 years up in orbit as part of this QB50. It was one of the most successful satellites there. And it also provided very valuable space heritage for the small gecko sensor, optical sensor. Sense are occupying a very similar space and also providing these very, I would say, leading edge optical sensors that through some clever design have allowed us to really up the optical sensor potential on these small platforms. We then go into capabilities that look at more kind of a vertical integration with the IT and selling space as a service. And this is Astrofika, who have been very successful internationally. And one of the most attractive things about Astrofika has been a very forward-looking internship program and the training aspect. And that's obviously something that SANSA would like to engage very wholeheartedly on with industry. There's also a sector of the industry that deals with the manufacture of very high quality CubeSpace components. So this is the ADCS aspect. This is a company called NewSpace, which is already providing subcomponents into various nanosatellite constellations, and a company called CubeSpace. And you'll see that pretty much all of the South African CubeSats that have flown have used CubeSpace ADCS systems. There's ongoing projects to integrate those with the optics. There's been very successful uptake on international platforms. And there's also, again, a forward-looking training aspect with regard to university engagement and internship, which is important. Okay, so South Africa has this strong industry capability. It has a very strong interest in the domestic missions. It's got a very strong interest in the collaborative missions. But we have to go through our domestic requirements process. This will, I think, take in the region of about 8 to 12 months. What's very likely is we'll be focusing on some variants of high resolution optical, hyper or multispectral optical, in other words, radiometric missions and machine-to-machine aspects. Our own feeling is once we've gone through our own user requirements process and we know what we want, we're then in a much better situation to engage on collaborative constellations, which we would see as primarily being the deployment of one's own assets into a constellation given some kind of minimum requirement. But we already see a very good potential for any of the science development, for example, the hyperspectral development. So I just want to finish with a couple of slides around, Roger talked about the second and third wave and the move to operational. And, to have a think about some of the trade-offs, we know many of the good things about CubeSats, but of course, you're not going to have the same capabilities on a 5 to 10 kilogram bus that you do on something that's hundreds of kilos to tons. And particularly the kind of payload functionality, for example, the downlink aspects. I saw there was already a question about if you've got a hyperspectral sensor, how on earth do you offload all your data? This is a fairly well-known aspect. So, we want to query some of these. And because I come from an optical background, we started looking at this. So the triangle on the left is a very typical kind of, mostly in CubeSat space in terms of constellations, particularly private sector new space, you're focusing on the fact that you're getting to very high revisit and very good coverage space. But the quality of information on the optical side and on the green here is the M2M side, has been focused on less. So if, for example, we're looking at putting VDES sensors on these small form factor buses, there's concerns about the capacity, the latency, the throughput, etc., the antenna capabilities. And of course, there's a classic trade-off in optical space between things like ground resolution, spectral resolution, signal to noise ratio. So These will depend on things like, what's your mission? Because obviously a vegetation mission might have an albedo of, let's say, 10 to 15%, and a water mission has an albedo of 1%. So that dramatically changes your sensor requirements. As I said before, talking about EnSight, you've actually got to be very, very aware of the fact that you might be using a jittery platform that is small mass, and this is going to affect your optical capability, particularly if you're looking at doing some kind of TDI, time delay integration to kind of drive up your signal to noise, etc. And then there are other bus concerns around, the downlink, the data throughput. Can you do some onboard processing? I think ESA's HyperScout was doing at least some cloud removal using onboard processing, which was a great step. And then the question is, if you take, for example, Sentinel-2, which is obviously not a hyperspectral mission, but is probably the highest resolution free sensor, you have an uncertainty there of about 5%. Now, how much money and how big and what other constraints are you going to have to overcome to get to, for example, even a 10% uncertainty with small sat missions. Okay, so just to wrap up, SANSA, it's a very exciting time right now. It's very dynamic. We're going into this intensive development stage. We do need to figure out what we're actually doing, and there's a process to go through that. And at the end of that process, we'll have a much better idea of our own missions. Subsequent to that, there'll be a very strong interest in looking at a collaborative constellation. And lastly, we are looking at a series of research calls. There'll be a call coming out in the next few months about the hyperspectral developments, synthetic data sets, etc., that are designed to allow us to be much better informed with regard to hyper multispectral sensor design. And obviously there's a lot of space for collaboration in there, and we're already looking at driving an active collaboration with NASA. And thank you very much, Andre. Thank you for bearing with me. I'm aware I've overshot my time slightly, and back to you.
Thanks, Stewart. Very interesting presentation. I think we're now ready to have Ernest deliver his presentation.
Yeah, can you hear me now?
Perfect.
Great. I think I had to hook on to a different network, hoping it will be better. So, all right. So I just want to give a talk on how the GhanaSat-1 project has evolved to an African Constellation satellite project. Next slide. All right, so I just want to give a brief introduction to the All Nations University. It's a private university in Ghana, and it has a very strong engineering department. Next slide. I wish I was controlling the slides myself, but that is okay. All right, so our laboratory is called the Space Systems Technology Laboratory. And in 2015, we had a collaboration with NASA to operate the aerosol robotic network, which is, it measures atmospheric aerosol. And that is the only robot in Ghana, which I personally manage that, that station. And in 2014, our lab also established the ground station, which so far has been able to communicate with more than 30 satellites passing over Ghana. In 2013, we did the educational project, which is actually the CoLab. Next slide. Great. So let me quickly give an introduction of the GhanaSat-1, which was launched in 3rd June 2017. It was a 1U CubeSat. It was launched to low Earth orbit, and the mission was actually Earth observation, and we had low and high resolution camera for the Earth observation. So actually the mission has ended because the mission life was 1 year and 8 months. So that's the 3 engineers, including myself, who developed the Ghana's first satellite, GhanaSat-1. Next slide. All right, so the story behind is that this is the first satellite developed by trained engineers from Ghana, and we actually started the whole process from a whiteboard, and with time we were able to develop the satellite. So you can just scroll through the pictures, following, just scroll through, just go forward. Yeah, Jose, just scroll through the pictures. Hello, can you hear me? Hello?
Yeah, sorry for just a second, because I mean there's a problem here in the presentation. I will go back. I will try again.
Yes. Hello? Hello, can you all hear me?
Yes, Ernest, there is a lot of background noise. I'm not sure if you can move to a different place or reduce it. I think it's a little bit better now.
Okay.
Thank you.
Okay, so we can just scroll through the pictures. So this is the developmental phases of the satellite. So we did our best to develop capacity and capability by doing it ourselves. So you can see the process of the development of Ghana's first satellite. Please scroll. Yeah, just scroll up. Just scroll up. Yes. So that's actually the Ghana's coat of arms on the satellites. Just scroll up. Just scroll up. Yes. Just scroll up. Yes, just scroll up. Yes, so good. Right. So let me quickly introduce the African Constellation Satellite Project. So after we achieved GhanaSat-1 and gaining the experience and the technical know-how on 1U CubeSat, we decided to bring some African countries together to develop their own satellites. So 2 years after GhanaSat-1, we started the AFCONSAT project. And what we did is that we threw an invitation to different African countries, sub-Saharan African countries. And then we threw the challenge to them for them to develop their own satellites. Next slide. All right, so the vision of the African Constellation Satellite Project is to create a network for African scientists and engineers to work together to design and build satellites to foster African development. Yes, so next slide. Great, so I'll just skip through this. And what we actually want to achieve is we want to develop human capital as a resource for the continent to pursue space missions. So that is what we are actually doing. Because of my time, just scroll down. Yeah, so the main objective of the project is for these countries. They have not yet developed a satellite. They have not yet gone to space. So looking at our experience and our exposure, we want to lead them to go to space. So to enable each participating country to develop and build their first satellite. So that is the main objective of the AFCONSAT project. Next slide. And not only the satellite, but then we are also looking at a ground station network, which is going to operate the satellite. So that is the scope of the AFCONSAT project. Next slide. All right, so in 2019, November, we had a number of countries signing an MOU for the AFCONSAT project. So currently we have about 9 countries, sub-Saharan African countries, who are on the project. Next slide. So here you can see Burkina Faso. The pictures you are seeing is the MOU signing ceremony, which was held in Ghana, All Nations University. So these are actually engineers and scientists from Burkina Faso. Next slide. Next slide. Okay, so let me keep talking as he puts on the slide. So we had engineers from Burkina Faso, and we also had engineers from Togo, and we had engineers from Sierra Leone, and we had engineers from Cote d'Ivoire, and we had engineers from Cape Verde, and also we are having engineers from Senegal and Botswana and Uganda. So these are actually institutions that want to spearhead the development of the first satellites for yeah. But interestingly, we have the project demonstration. So what I mean is, in code, all they want to do is to just go to space as the first institution for their country, or that they want to build the first satellite for their countries. So we've had a battle over the mission, because in the scope of AFCONSAT, all the satellites, all the Constellation satellites, 7 or 9 of the satellites are supposed to operate on the same mission. They are going to carry the same mission, and each participating country has its different mission. So some have climate action, and some also are looking at Earth observation and diverse kinds of missions. So it has been some battle to try to settle on which mission to go on to. So for now, I will say that what we have is engineers who are willing to generate or to get some funds to go to space. But then we want to get that kind of mission that can be applicable to all. Looking at all the missions that were submitted, we saw that the climate action mission is what applies to almost all the countries. So we're actually looking at key players or organizations in climate action, so that you can suggest to us a payload or the kind of subsystem that we can actually use for this African Constellation satellite project. So for now, we have these 9 countries, and then we are trying to get a common payload for climate action. Yeah, so actually that is the stage we are now. For funding, we are putting in joint funding requests to African Development Bank, and that it's been a little progressive, though there has been some delay, but hopefully we should get some funding by the end of this year. And actually, when we started the project in 2019, our vision was according to the timeline, we were supposed to go to space. The 7 or 9 satellites were supposed to go to space by 2021. But then there's been a delay because of COVID-19. So we are looking at 2022, June, we should be able to go to space. So that is actually the progress we have for the African Constellation Satellite project. And actually we have a number of countries who want to sign in to this project because they believe the All Nations University in Ghana is able to help them to develop 1U CubeSat. And actually we don't develop commercial off-the-shelf systems. So I'm also looking for partners, those who can provide subsystems for this huge project. So that is my short presentation, and I couldn't include more slides because we've been working on other projects and then we've been on and off our lab. So that is the group picture. You can see the different countries representing, and this was the MOU signing ceremony. So for now, some of the countries are actually already building their ground station to operate the satellites, which we are also offering to guide them in that. So we are actually looking at collaborations and other developers to come on board. But then the main need that we have now is a climate action payload. So if your company is able to suggest to us a payload for we are looking at 1U. No, we are looking at a 2U CubeSat. If your company is able to suggest to us a payload for climate action for 2U, I think we'll be able to work together. So that is my contact. You can contact me anytime, and we are hoping to work with anyone interested in this project. Thank you very much.
Thank you, Ernest. Very interesting presentation. We will now pass the floor to Miguel Bello, the CEO of AIR. Miguel, the floor is yours.
Thank you, André. First of all, thank you very much to those impressive presentations from Roger, Milton, Stewart, and Ernest. We show us the landscape of nanosat in 3 continents. Thank you very much. And before going to the Q&A session, I would like to recall that within the ESA Center, we have the Atlantic Constellation as one of our flagship projects. It was already mentioned by Milton in his presentation. We aim at the ESA Center to develop a constellation between several country members of the ESA Center in Africa, in America, and in Europe, to be able to deal with the problems of the Atlantic needs, with the ocean pollution, with optimization of agriculture, fisheries, climate change. This constellation, the idea is to complement the existing satellite, the existing Copernicus, the existing big satellites from US and Europe and Brazil. The idea is to give frequent data. We can be able to provide very frequent data every few hours, because those sophisticated satellites sometimes have revisit time of the order of weeks. That means our idea is to complement the existing satellites and with different types of sensors. We already discussed, Roger presented the GNSS reflectometry, hyperspectral, Stuart as well talk about different sensors. Our idea is to make a constellation. We have the beauty of giving the full power of a constellation to every single country with a cost which is a fraction, because it is built by combination and a joint effort of several countries of the ESA Center. We are at the initial phase of that. For this, we will start a consultation process. We will start with the requirements. We did a preliminary work, but this is just preliminary. we will ask in the next weeks to the different countries at the Air Center for what are the needs, what is the priority of the needs, which is the beginning for the design of the constellation. On the Portuguese side, the process already started. This is obviously in combination with the Portuguese Space Agency. Portuguese Space Agency already started some preliminary activities with the European Space Agency within the INCUBE projects. This is now moving, some proposals on the table, and we will do this in collaboration. The idea is to develop all the satellites, not to share given application and data to the countries, but also the capabilities of the countries to be used in the development of the constellation. I just wanted to tell that because this is going to happen in the next weeks, and we will contact all the country members of the Air Center. Thank you very much. And I think, André, we can go now to the Q&A session.
Thank you, Miguel. Just before going to the Q&A, we'd like to give special thanks to Brian Melton from the European States Environmental Protection Agency and Bryce Monfrey, team leader at African Union, for helping the Air Center to disseminate the Networking Friday sessions and mobilizing attendees. So thank you very much. Moving on to the Q&A. I've seen that we have quite a few questions in the Q&A window. Some of them focus on similar aspects, so I'm going to try and group them to see if we can answer everyone in the time that we have left. And there were a couple of them focusing on collaboration opportunities, funding and support for academic development, for the involvement of young scientists, especially with marine backgrounds, and collaboration with educational programs in Africa, as well as involvement of ESA with the ongoing initiatives for pollution monitoring in the Atlantic. So perhaps I would start with Roger, especially concerning the potential collaboration or involvement of countries and institutions with ESA activities, and then move on to the other panelists.
Okay, so yeah, which question then should I answer, Andre?
So what are the funding and support opportunities that ESA has for academic development with CubeSats, and also how is ESA getting involved or cooperating with other ongoing initiatives in the Atlantic to do specifically pollution monitoring?
Okay, certainly I could answer the question about funding opportunities or support opportunities for academia to get involved in CubeSat development. At ESA, we do have for European universities our Fly Your Satellite program that's run by our education office. The Fly Your Satellite program actually offers also launch opportunities for CubeSats developed at universities for hands-on education purposes. Plus also in our technology program, when we develop CubeSats for technology demonstration purposes, we do have universities involved in those projects, teaming up normally with industry. So that's normally on the research side of universities. It can also include the scientific support to those projects. So when we do technology demonstration missions, for instance, for the reflectometry one, which I mentioned, is foreseen to have a scientific community support to that, to benefit from the data, reflectometry data over the oceans. We do have our Earth observation program in ESA, which has recently, the program brought out a call for a mission called Scout. So there was an open call for, let's say, the Earth science community in conjunction with CubeSat system integrators to propose new mission concepts addressing let's say the priorities defined in Earth science in Europe, and there were very many good proposals to this call. In the end, there were I think 4 parallel mission concept studies awarded, and those are completed now, and one has been selected to go forward for development as a 30 million euro mission. It's called the Scout mission, and that will actually be addressing, I think, this first mission, atmospheric science and constituents, including pollution, of course. So that looks to be of great interest to the community, and so I think those that are engaged in oceanography and marine science could look at those kinds of opportunities, particularly in the Earth observation program, now getting more engaged in CubeSat missions, and actually those calls include the possibility to have constellations, so within that budget envelope. So I think the one that's selected, in fact, was a 3-satellite constellation, but in principle it's completely open. So I think there are a growing number of opportunities now through our various programs in ESA for scientists, but also those that are developing CubeSats on the engineering side.
Thanks, Roger. Is there a particular website or web page in the ESA website that people can refer to if they want to find out more?
Yes, certainly. There are probably 3 links I could make available. I don't know how you'd like to make those available, but I can certainly send them to you so you could.
Perfect. I think if we can share them in the chat, that would be perfect. Afterwards, I think probably you can also publish them in the site.
Okay, happy to do that.
Many thanks. Regarding, there was another question about collaboration on educational programs with African countries. And I think here, if I understood correctly, the AFCONSAT seems like a good initiative, but perhaps Ernest and Stewart might want to add something.
Okay, I'll happily go first. Yeah, so AFCONSAT is terrific. There's an emerging initiative called the Pan-African University Institute of Space Science. Now, this will be based in South Africa, primarily at the Cape Peninsula University of Technology. It hasn't started yet. It's anticipated to start next year. And that is anticipating holding a Pan-African, effectively a master's degree in mission analysis and design. So obviously that's an engineering focused degree. CPUT obviously is running that master's program anyway, so that could be applied to. I think there are several other South African universities that have the engineering aspect covered. SANSA has a series of tech challenges, innovation capabilities, opportunities, bursary opportunities, etc. I think some of those may be restricted to South Africans. But one word of advice I guess I could offer is that if you're interested in educational opportunities in the application domain, so say you're interested in the marine science, the nanosatellite aspect at the moment is very much in development, and most of the exciting work is around mission involvement and the engineering side of things. So if you're interested in the application domain itself, rather go through much more established mechanisms to Copernicus, etc., to the actual large operational satellites that are providing very, very high quality data already. And, don't focus so much on the nanosatellites. If you're interested is in mission involvement per se, then obviously the nanosatellite aspects are a way to go. And I can try and post some SANSA links afterwards to help with any opportunities. Thanks.
Thank you, Stewart. Ernest, do you want to add anything?
Well, for now, no. We are actually also looking at funding opportunities for academia and that, and more so we are also looking at commercial off-the-shelf subsystems developers who can propose subsystems for AFCONSAT. And moreover, more countries are joining for AFCONSAT, and any other country will sign in for the project. So for now, those are the few comments I have. I will get the email of the key players, the key participants from Jose, and then I will send a follow-up mail if needed. Thank you very much.
Thank you. We have another question from, I think, several people concerning the differences and the constraints and limitations of nanosats, and in particular CubeSats, with respect to their larger brethren. So I know Stewart covered part of this in his presentation, and I think Roger also. Do you guys want to add anything to the slides that you have already presented in terms of, precision, resolution? Are they mostly complementary or good for search capacity? And perhaps I'll add just a bit on my side. Can we envisage in the future a large ensemble of CubeSats replacing a single larger satellite anytime soon, or is it still, or are we still too far away?
I'll let Roger go first.
Sure. Yes, it's a very interesting topic, I think, and thanks for the question. I would say that, of course, as I highlighted, CubeSats offer they do offer an affordable way to field constellations, potentially of tens or hundreds of satellites in low Earth orbits, to provide global coverage and fast revisit times, let's say. So those are the main advantages, although I think one needs to look at the phenomena that's to be observed for Earth observation. For instance, vegetation changes on the Earth land mass probably they don't have very rapid changes, so even a twice per week revisit would be okay. But there are other observables for constellations like methane emissions and other anthropogenic gases like NO2, for instance, which have very short time scales, so typically of the order of an hour or so. So in that case, having a constellation of tens of satellites distributed in different planes that can provide relatively high resolution data for NO2, for instance, on the order of a kilometer or so resolution or less, but provided at several times throughout the day for a particular city, is a capability which is just not available today from any satellite mission. So even large missions. So that there are significant advantages, let's say, in certain areas. I think when it comes, obviously there are drawbacks, and Milton has, Stewart has also highlighted them in his presentation, that with small satellites, when it comes to optical imagery, for simply providing imagery, let's say, you're limited on the aperture size, and the SNR is quite reduced, and you do get lower image quality generally than larger satellites. So there are constraints on the imagery side. Typically, you could get 1, 2, 3, well, let's say around 3 meters imagery from a constellation on a very regular basis, such as what is offered by the Planet constellation. So CubeSats won't do everything. There are niche applications that they can serve, and I think, as I mentioned, NO2 and methane observations are one of them, plus radio occultation data for measurements, meteorological measurements to feed into for weather prediction models. Radio occultation is one of the main sources of source data for weather prediction, and with those measurements you can get temperature, pressure, humidity to feed in, and the more observations you get, the better per day. So a constellation of CubeSats providing those measurements, which is feasible, and that's what Spire are doing with their constellation. That is a very good example of RF. Is also, as I highlighted, reflectometry can provide a lot of coverage of sea surface states from a constellation. So I think that's another area of good advantage. Just to answer the question of will CubeSats replace one big satellite, I think they're very much complementary. However, there is one case we're studying at the moment, which may see a number of CubeSats replace a larger mission, and that's for, again, for oceanography. That's so, if you can imagine a mission like the SWAT mission, which is a very large mission, it's providing a radar-based altimetry measurement, very high precision, with long deployed booms from the satellite, and giving an interferometric measurement. We're looking at actually a formation of 4 CubeSats, 12-unit CubeSats flying together and providing a similar measurements, but obviously not fixed together on a boom. They're free flying, providing a sparse aperture. And it seems, at least according to the initial studies that have been done, a similar relative altimetry accuracy could be achieved, albeit at lower cost, of course, with the CubeSat formation. There are some caveats to that. It won't cover everything that SWAT could, but there's a certain, I think, number of measurements which could be achieved of interest to the oceanography community.
Thanks, Roger. Stewart, do you want to add?
I think Roger's pretty much said most of it. Again, I would say, yeah, CubeSats are complementary. So the key advantage is really in your ability to get to new time and space scales, but you are paying quite a compromise in terms of the functionality of your sensors and their ability to pick up signals. So the key thing is to understand the event scale of the phenomena you wish to observe, and then I think also see if you can come up with some creative aspect of how to deal with it that maybe overcomes some of the CubeSat limitations. So, for example, we had a experimental sensor called a K-line sensor on the ZA Cube 2, which looked at using cheap commercial technology, looked at the potassium emission spectrum using 2 bands to look at fires. So you might, for example, the oceans, as obviously the atmosphere is probably the quickest, the fastest changing system, but the ocean changes very quickly too. So certainly oceanographers would be very, very interested in, a 2 or 4 hour repeat time with a good enough signal for temperature, thermal, or some of the radar-based applications. But I think right now we haven't quite got the miniaturized sensor technology to the stage where you getting anywhere near the same quality of data. But a bit of creative thinking. So Roger's SWAT replacement is a terrific example of that.
André, may I add
Sure.
one or two comments? So I think that Roger and Stewart, they have addressed this topic in a very systematic and didactic way, but I could mention and also agree with them to see the nanosats and nanosats constellations as complementary to the existing satellites. But, and as Roger mentioned, you have some niches of applications with a much higher temporal resolutions or visit if you wish, and for example, for land cover land use in the coastal zone, you can detect changes very easily. Also for inland waters, you can get, and coastal waters, you can get higher spatial resolutions. So where most of the times waters, they can be more optically complex, which is an issue for signal to noise ratios, but you can also have higher signals. So there is a huge potential to be explored, for example, taking not very new, but different approaches, such as feature extraction and other types of artificial intelligence and so on, to explore this data, which is going to be provided. It is already being provided. So that's my 2 comments for now.
Thank you. I think we may have time for 1, possibly 2 questions. There was an attendee who asked about, so we're talking about a large number of constellations. There are some already flying, others are in the works. How does this all fit with debris generation from nanosatellites?
Yes, I could perhaps answer that. I was doing space debris research for 8 years, I think, in my past career, so fairly qualified, although that was some time ago. Yes, it's true. I think, of course, there is this concern that many constellations being deployed, each of tens to hundreds of CubeSats, could add to the space debris problem in low Earth orbit. I mean, first of all, one has to look at the modeling predictions, what the models predict for the coming 100 years or so in terms of what happens when you start adding these types of, or numbers of constellations into orbits between 500 to 600 kilometers, because that's where they usually will be. And the modeling research that has been done the last few years at ESA says that the environment currently will tolerate up to 300-400 CubeSats launched per year into LEO before they start to have a noticeable effect on the space debris population over the next century. But obviously, we've reached that stage quite quickly, and we're now seeing numbers of launches per year getting towards that level. So all constellations will have to comply anyway with space debris mitigation requirements and international guidelines. So that means ensuring that the satellites re-enter within 25 years. And that's the assumption taken with this modeling. So 300 to 400 per year, assuming they're all coming down within 25 years. But I think as soon as we start to see numbers higher than this, the space debris community, those that are doing the modeling, will need to look again to see what additional measures are necessary, maybe more stringent measures to ensure that the on-orbit collision risk is minimized. I have to say we're trying to do what we can on the technology side as well. So we are bringing in technology demonstration missions with propulsion on board. GOMEX-4, I mentioned, successfully demonstrated orbit control, and with that capability you can do collision avoidance maneuvers. Also GOMEX-5, which is coming up next year, that will be demonstrating electric propulsion for large orbit changes, and particularly for deorbiting. So I think what needs to be borne in mind when deploying these constellations is we should have some means on board to do collision avoidance and deorbit at end of life to drastically reduce the lifetime. I think that's the responsible thing to do.
Thanks, Roger. I'd like to leave one question of my own, which I think is applicable to all the panelists, and I hope the attendees also find it interesting. We were just talking about constellations. Miguel presented the Atlantic constellation, and there are a few of them. They're very trendy right now, and while it may be easier to fund one if there is a strong business case behind, how does the panel see potential collaboration and governance models for constellations that involve multiple countries or entities? So I think that's, in addition to the technical challenges, that's a different challenge, having a constellation that provides for a number of different countries or entities and is run also by a different set of countries or entities. Just to hear your thoughts on that.
Well, maybe I can jump ahead on this, just a few comments again. Well, I think that there are already some constellations, and you should mention, for example, the International Charter for Disasters Mitigation. So there is a lot of international coordination for doing this, and also have the CEOS virtual constellations. So I think that those are good examples of ongoing approaches for dealing with that. Of course, and for specific cases, you're gonna have to have other discussions in terms of, I don't know, data policy, which type of access each member or interested country or agency or institution will have, how you're gonna facilitate that, and so on. So, but I think that so those concepts, they already exist. So we should build on previous experience. That would be my suggestion.
Thanks, Milton.
Okay, and maybe for ESA, well, of course, European Space Agency, we do have the possibility to have cooperation agreements with other space agencies, and we have quite a number of those in various domains, of course, within the space sector, and there is always that possibility. Also on the program side, there are various programs in ESA that are able to support one or more ESA member states to participate in schemes for joint missions, let's say. So I think there are possibilities there. I just wanted to highlight probably in the CubeSat domain, the best example so far was mentioned a couple of times, the QB50 constellation, and that's obviously been a project funded by the European Commission, where, of course, universities were providing CubeSats from all over the world. So I think it was a very good example of an international collaboration, mostly with universities, of course. But just as a question, could it be considered as a collaboration between agencies or industry?
So from my perspective, I think the answer kind of depends what you're trying to achieve. So as Roger said, QB50 is a good example. Now that was, an experimental constellation. So you're not looking to get, the impact you're looking for is not constellation scaling for operational purposes. In other words, to get to, your 4-hour repeat time with some systematic observation. So that kind of collaboration, I think, is much easier to realize in some ways than an operational constellation. Now, when you get to operational, I think the first thing you have to understand is, why are countries investing in the satellite build? And certainly, depending which country you look at, so, if you look at, say, Copernicus, for example, obviously there's a huge investment in the aerospace industry that is nationally important to Europe. So the direct investment is important in its own right, but so is the downstream investment, and the fact that making all of this Earth observation data is, you know, a massive economic value creation step in its own right. But so to my mind, the key thing is first of all to realize that, and realize that, you know, you have to investigate each country's own reason for the satellite build. In most countries, and I don't mean to speak for Milton, but for example, Brazil and South Africa would want to have their constellations, I think, and Milton, I'm sure, will correct me if I'm wrong, built by Brazilian or South African engineers to make our own space industries more competitive, as would the US, Canada, Europe, etc. So the collaboration can't come from a commercial sell of satellites to different countries. I think it must come from a minimum constellation specification, and then, you know, Europe or let's say Portugal decides it can contribute 6 satellites to the constellation, and South Africa contributes 4, etc. And you come to some orbital arrangement and some ground segment arrangement, and you come to some understanding that maybe one of the sensors on the satellites will either be the same sensor or similarly enough configured, and you're going to use similar approaches in terms of the processing. So something like that. But I think this understanding of why countries are investing is the first thing you've got to do to then figure out how to build a operational collaboration.
Another interesting example, André, for Constellation, international Constellation, was a disaster monitoring constellation. It was made up to 4 satellites, one from UK, one from Spain, one from Nigeria, one from Algeria. Was 2 European countries with 2 African countries, but even more complex, 2 private missions financed by private companies and 2 governmental missions. It's also a public-private partnership, which is also something complex that we have to analyze. Then there are cases that we will take as examples for the Atlantic Constellation, for instance.
Many thanks. I think we're close to wrapping up. Maybe just one very final question. Let me just go through the different questions. I think there were some questions regarding specific sensing capabilities of nanosats. There is one in particular which is kind of popped up, which is related to how do we use the remote sensing sensors to represent reality? Are these enough? Should we do we need to combine them with in situ or touching the ocean or the thing that we're measuring in order to understand the ocean processes?
I can also jump ahead of this. Sorry for that. Of course, I mean, as an oceanographer, we know from the very beginning that you must rely in observations, both from orbital or remote sensing sensors, if you wish, from different altitudes, and from in situ observations, of course, 3-dimensional observations, especially, and also in modeling. So those are the 3 main legs that they belongs together. So that would be my opinion or vision.
Thanks, Milton.
Yeah, maybe just to add to what Milton said, to calibrate and validate sensors is obviously a very important point for an operational constellation to actually give accurate, absolute accurate truth data, and doing that for ocean observations, yes, for sure, having in situ measurements on the ocean surface helps. There are also, I think, standard sites that can be observed as well for calibration, but having, let's say, buoys in the ocean to do the sampling one must also get the data back from the buoys. So if that's to be done in a real-time system or on a short time scale, then perhaps one needs another constellation or part of the constellation to get that data back from the surface. So I know there are M2M solutions being developed, this narrowband IoT type solutions or the VDES protocol type solutions to get surface data back from buoys through the space domain, through a constellation and back to users to, let's say, compare with the space-based sensor data.
Yeah, I think for me it comes down to a classic time, space, and quality of information kind of approach, but you actually have to look at the event scale of what you're looking at. So let's say you want to capture the spring bloom in the Atlantic and carbon sequestration and what impact that's having over 50 years. So you ideally want to be able to say, okay, the phenomena we're looking at, which is, you know, the phytoplankton growth and the carbon sequestration, you need ideally to be measuring kind of sub-kilometer every few hours, and you need these kind of physical things with an error of no more than 30%. So a satellite is only going to give you snapshots of that. It might give you many decades of information, but at quite a coarse scale. So you're going to have to try and bring in other observation technologies, buoys, Argo floats, gliders, whatever, to try and get another suboptimal snapshot, but at different time, space, and error scales. And ideally, you'd bring a model to play as well, so that would, which would have its own error. And you now then have to try and fit all of this together to understand what's going on. So there is no perfect observation system, but having more observation systems at different scales with different errors and different capabilities give you more knowledge. Then it comes down to budget.
Andrea, I also would like to point out that definitely such an initiative of having Atlantic or any other type of nanosats constellations is a huge, will be a huge achievement, and with a lot of technological development. However, it's also maybe important to think about, once the data is available, who or how the data will be transformed into, processed into information, and then services and applications of knowledge, if you wish, from a scientific point of view. So although maybe you're gonna have to go into parts and phases, should keep that in mind since the very beginning. So because maybe other members or partners of this initiative, they could be adding value and effort for using the data which will be made available from this type of initiative, such as a constellation, and developing application services and or increasing our scientific knowledge. So that's what I also consider very important to consider.
Definitely. Thank you. Thank you all. I think just to close on my side, the Air Center is going to share the questions that were posed during the session with the panel. So we will be able to answer any outstanding questions by email. Any last round of comments from the panel? From my side, it was a pleasure to moderate the session. Any final comments, thoughts?
Just to say thank you very much. It was a pleasure, and I look forward to more engagement on collaborative constellations, because I think this could have huge value if we can get it right, but we have some political, technical, economic, and scientific mazes to work our way through to make it happen.
Okay, well, from the ESA Center, thanks very much to all panelists and to all attendants. I think this has been a record of attendance, a high interest in this topic, and it has been an outstanding presentation by all of you. Thank you very much indeed.
Thank you. Thanks for the invitation.
Thank you very much for the invitation and for my colleagues. and also for the audience.